There is, in the wall of your left ventricle, an iron atom. Just one. Not the most important one, not the most special one, simply one of the many trillions of iron atoms sitting in the muscle of your heart at this exact moment. It is held inside a small folded protein called myoglobin. The protein is wrapped around the iron the way a hand cups itself around a candle in the wind. The atom has been waiting, perhaps a few milliseconds, for a passing oxygen molecule. It is about to catch one. It will hold the oxygen for 2 or 3 seconds, hand it off to a hungry mitochondrion, and wait for the next. Now, where has this atom been before today? I want to take you on a small trip. Backwards in time, following one iron atom from the wall of your ventricle to the place it was made. We will pass through some graveyards along the way. The atom has seen all of them. Let us first look at the place this atom lives. The heart, you see, is not really one organ. It is 2 pumps stuck together, side by side, beating in time. The right side takes the tired blue blood coming back from your toes and from your liver and from the back of your skull and sends it the short distance to the lungs. The left side takes the blood the lungs have just refreshed and shoots it out with considerable force to every cell in your body. The wall of the left ventricle is the thick one. It is about 1.5 centimeters deep in the adult human, made of cells called cardiomyocytes, packed together like bricks but lined up so their fibers all pull in the same direction. When the wave of electrical excitation sweeps across them, they all squeeze at once. That is the squeeze you can feel under your fingertip when you press against the side of your neck. Inside each cardiomyocyte are little engines called mitochondria, thousands of them in each cell. They are burning sugar and fat, slowly in the presence of oxygen, to make the energy that drives the squeeze. They need oxygen the way a fire needs oxygen, and the iron in myoglobin is the little buffer that holds a quick reserve of oxygen right inside the muscle, ready to feed the fire between heartbeats. So that is where the atom lives. In a fold of protein, inside a muscle cell, inside the thickest wall of the central organ in your chest, a particular place, a specific address, behind the breastbone, slightly to the left, about the size of your closed fist. Now let us begin the trip backwards. Before this atom was in your heart, it was, perhaps, in your dinner. You ate a piece of red meat last week, or some lentils, or an egg yolk. Some plant or some animal had taken iron from the soil or from another organism, and you, in turn, took it from them. The iron walked from your stomach into the cells lining your small intestine. It was bound to a transport protein called transferrin and shipped through the bloodstream. Cells in your bone marrow, the ones busy building new red blood cells at the rate of about 2.5 million per second, grabbed some of the iron and tucked it into the heme groups they were building. Other iron, like the atom we are following, ended up in the heart, woven into myoglobin during the slow renewal of cardiac muscle. But this is recent history. We have only traveled back a few weeks. Before it was in your dinner, the iron was in the soil, or in a cow that ate the grass that grew in the soil, or in the plankton in the ocean that was eaten by the fish that was caught in the sea, that was salted and shipped, and so on. The iron of the biosphere is a small pool, by mass. Most of the iron on Earth is locked away in the planet's core, where you cannot touch it. The iron that is alive, that moves between bacteria and grass and worms and birds and elephants and people, is a smaller circulation. The same atoms move through this circulation again and again. A single iron atom in the topsoil of a Kansas wheat field may, over the course of a few centuries, pass through the hemoglobin of 1,000 prairie animals. And here is the part I want you to sit with for a moment. The iron in your heart, right now, has almost certainly been inside another beating heart. Maybe many. Maybe an ox that pulled a plow in Mesopotamia. Maybe a soldier in some forgotten war. Maybe a child who died of fever in a village whose name you would not recognize. Maybe a horse, a deer, a sparrow. The atom did not care which heart it was in. It does not remember. It just does its little chemical job, catching oxygen and letting go. But the atom was there. Atoms persist. The body that holds them for a little while does not. Now, this is not metaphor. This is bookkeeping. Atoms are conserved at any temperature a body experiences. The iron atom that beat in the heart of a Roman legionnaire did not vanish when he died. It was buried with him. The body decayed. Bacteria broke open his cells. The iron, freed from the corpse, was washed by rain into the soil. A plant root took it up. An insect ate the plant. A bird ate the insect. And on, through the long, quiet recycling that the earth has been performing for, well, since there were things to be recycled. The atom in your ventricle has, by very simple arithmetic, witnessed an enormous number of deaths. Not because it is special. Because it has been around for a very long time, doing one small job in one body after another. But I have not yet taken you back far enough. Because before the iron was in any heart at all, it was in a star. And this is the part that I would like to slow down for. Because it is, in some sense, the strangest part of the whole story. The iron in your blood was not made on the earth. The earth cannot make iron. No process on this planet can fuse lighter elements into iron. The only places in the universe that can build iron atoms are the cores of dying massive stars and the few seconds of a supernova explosion. Look at this. Margaret Burbage, Geoffrey Burbage, William Fowler, and Fred Hoyle, working between Cambridge and Caltech in the middle of the 1950s, wrote a single long paper that explained where every element heavier than helium comes from. It was published in Reviews of Modern Physics in 1957. Everyone in the field calls it B²FH, after the initials of the four authors. In that paper, they laid out the processes. Hydrogen fuses to helium, helium to carbon, carbon to oxygen, then to neon, then to silicon. And silicon, in the last desperate hours of a dying massive star, fuses up the ladder all the way to iron. But here is the trouble with iron. Iron is the most tightly bound nucleus on the chart. To fuse it into anything heavier costs energy instead of releasing it. So when a star's core becomes mostly iron, the fire that has been holding the star up against its own gravity flickers out. The core collapses. In about 1 second, an object the size of the Earth falls inward until it is the size of a city. The collapse releases enormous energy in the form of neutrinos and pressure and light, and the rest of the star is blown outward at a fraction of the speed of light. That is what we call a supernova. And inside the wreckage, scattered across the new nebula, are the iron atoms that the star spent 10 million years making. One of those atoms is in your heart. Now, when I tell you this, you may not at first feel anything. The words go by quickly. The mind is good at letting them pass. So let us be specific. The sun is about 4.5 billion years old. It is a second-generation star, made from the debris of older stars that lived and died before it. The iron atoms that ended up in the dust cloud from which the sun and the planets formed had to have been forged in stars that died before our sun was even a glimmer. The iron in your left ventricle was made, at the earliest, perhaps 9 or 10 billion years ago. It then drifted, as part of a thin cloud of dust and gas, across hundreds of light years of empty space, for perhaps 3 or 4 billion years, until our sun ignited and the solar system condensed out of the remaining debris, with the iron settling, mostly, into the center of the Earth. Most of the Earth's iron is still down there. The planet is about 32% iron by mass. The core is mostly iron. Walk anywhere on the surface and there is, roughly 5,000 kilometers beneath you, a ball of mostly iron, hot enough to be liquid in the outer part and solid in the inner part, slowly turning, producing the magnetic field that keeps the solar wind from stripping away your atmosphere. You owe the magnetic field and the survival of your air to that iron core. The iron in your blood is, geochemically speaking, an emissary from below. The iron in your heart, then, was forged in a dying star, ejected in a supernova, drifted across the galaxy in a cold cloud, condensed into the planet you are standing on, sat somewhere in the outer shells of the early Earth, was weathered out by rain and ocean chemistry, was picked up by a single-celled organism a few billion years ago, and has been passing through living things ever since. The deaths of all those living things did not consume the atom. The atom outlived them, the way a brick outlives the houses it has been used to build. And here is a thing that follows directly from that. The proteins that hold iron in your blood and in your heart are old. Hemoglobin, the red protein in your red blood cells, is built on a chemical group called the porphyrin ring. The porphyrin ring is one of the oldest molecular inventions of life. The same ring with a different metal in the middle is the chlorophyll in every green leaf, which catches sunlight and runs photosynthesis. Put iron in the middle and you get heme, which catches oxygen and runs respiration. Plants and animals are, in this sense, running the same trick with different metals in the center of the same little wheel. The trick is at least 3 billion years old. Max Perutz, working at the Medical Research Council laboratory in Cambridge, spent 23 years solving the three-dimensional structure of hemoglobin by X-ray crystallography, and he published it in Nature in 1960. For that work, he shared the Nobel Prize. He showed that hemoglobin is 4 globin chains, each cradling a heme group, each heme group with a single iron atom at its center, and the 4 work together so that grabbing one oxygen makes the next 3 easier to grab. That cooperative grabbing is what lets a red blood cell pick up oxygen in a fraction of a second in the lung and drop it off just as quickly in a starving muscle. So the iron is old, the cradle that holds it is ancient, and every time you take a breath, every time the muscle of your heart squeezes, you are running a piece of stellar chemistry that has been spinning in one body or another since before there were bodies in the sense we usually mean. Now we come to the part of the story that I find it humbling, because the body does not throw any of this iron away. It refuses to. The body of an adult human contains, on average, between 3 and 4 grams of iron. About 2.5 grams of that is in the hemoglobin of red blood cells. A bit less than half a gram is in the myoglobin of muscle, including the cardiac muscle we have been talking about. The rest is in storage proteins called ferritin, mostly in the liver, the spleen, and the bone marrow, and in the iron-containing enzymes of every cell. 3 to 4 grams. That is about the mass of a small paperclip. That is all the iron you have. And it does the work of moving oxygen for 100 trillion cells. Now your red blood cells, the ones carrying the great bulk of the iron, only last about 120 days. So every day, roughly 1/120th of your blood breaks down. About 200 billion red blood cells expire per day. They are not flushed out. They are eaten. There are specialized cells called macrophages, mostly in the red pulp of the spleen and in the liver, whose job is to find old, stiff, slightly damaged red blood cells, swallow them, dismantle them, and recover the iron. The cells then ship the iron back into the blood plasma to be used again. The carrier protein is transferrin. The exporter from the macrophage is a channel called ferroportin. The whole operation moves about 25 milligrams of iron per day. By comparison, the entire diet of a healthy adult delivers only 1 or 2 milligrams. So your body is recycling about 10 to 20 times more iron per day than it is absorbing from food. The recycling is, by any honest measure, more than 90% of your daily iron supply. Now who, you might ask, is running this remarkable bookkeeping? Because the body cannot just open the floodgates. Too much iron in the blood and you generate free radicals and damaged tissue. Too little and the bone marrow cannot build red blood cells fast enough. There has to be a regulator. And there is. The regulator is a small peptide hormone called hepcidin. It is 25 amino acids long. It is made by the liver. It was discovered in the late 1990s by Thomas Ganz at the David Geffen School of Medicine at the University of California in Los Angeles, and described in detail in his paper in Blood in 2003. When iron levels in the plasma get too high, the liver secretes more hepcidin. Hepcidin binds to ferroportin, the iron export channel on macrophages and gut cells, and tells the channel to be pulled inside and destroyed. With the channel gone, iron stops being released into the bloodstream. Levels fall. When iron is low, hepcidin levels drop, the channels are restored, and the iron is allowed to flow again. It is a thermostat, a real peptide-based thermostat for the metal in your blood. I want you to feel the strangeness of this. The atoms that traveled across the galaxy, that were forged in a dying star, that were carried through how many bodies before yours, are now being managed every day by a 25 amino acid peptide running a feedback loop in your liver. And the recycling efficiency is on the order of 90%. There are industrial recycling plants that would weep at that number. Let us now visit one more part of this story, because it ties the cosmology to a very specific moment in human history. You see, the muscle cells in your heart, the cardiomyocytes themselves, are mostly old. Most of them have been with you since you were a small child, some of them perhaps since before you were born. But not all. About 1% of the cardiomyocytes in a young adult heart are replaced each year. The number drops with age, to about 1/3% by age 75. This was figured out by an extraordinary piece of work by Olaf Bergman, Jonas Friesen, and their colleagues at the Karolinska Institute in Stockholm, published in Science in 2009. They used something called the bomb pulse. Here is what they did. In the 1950s and early 60s, the United States and the Soviet Union and several other nations tested hundreds of nuclear weapons in the atmosphere. Those tests produced a spike of radioactive carbon-14 in the air. The carbon-14 mixed into the carbon dioxide of the atmosphere was taken up by plants, was eaten by animals, was eaten by people, and was built into the DNA of every new cell made during those years. Above-ground testing was largely halted by the Partial Test Ban Treaty in 1963. After that, the atmospheric carbon-14 fell, slowly year by year, as the oceans and the biosphere reabsorbed it. So if you measure the carbon-14 in the DNA of a cell, and you know the curve of atmospheric carbon-14 from 1955 onwards, you can ask, in what year was this cell born? Bergman and Friesen took heart tissue from people who had died, and they measured the carbon-14 in the DNA of the cardiomyocytes, and they computed the birth dates. They found that some of the cells were old, born around the patient's own birth, but some of the cells were younger. The pattern only made sense if cardiomyocytes were being replaced, slowly, all through life. Which means this. If you are old enough to have been alive during the atmospheric bomb tests, some of the carbon atoms in the DNA of your heart cells were forged not in a star, but in a fireball detonated above Bikini Atoll or above the Kazakh steppe. They drifted down. A plant ate them. You ate the plant. Your bone marrow used them. Your heart used them. And now they sit in the genetic code of cells that are, at this very moment, contracting under your sternum. So in one organ you carry the chemistry of two different cosmic events. The iron from supernovae 9 billion years gone. The carbon from human fission 3/4 of a century ago. Both are written into the same beating muscle. Both will, when you die, return to the soil and be picked up by something else. Now I want to pause here for a moment, because I have been telling you a great deal, and I want to be honest with you about what we know with what confidence. The stellar origin of iron is about as well established as anything in physics. We see the spectral lines of iron in supernova remnants. We see iron 56 abundances that match nucleosynthesis predictions. We can run the calculations on a computer and reproduce the observed abundance curve of the elements with great accuracy. This is a result you can put weight on. It is the bedrock. The recycling of iron through the biosphere over geological time is also a strong claim. The chemistry of how iron is held in the soil, picked up by roots, moved through the food chain is well measured. The thermodynamics demand it. The atoms have to go somewhere when an organism dies, and we can trace where. The claim that any one specific iron atom in your heart was previously in another particular heart, well, that is an inference. We cannot tag an iron atom and follow it. We can only argue from the size of the biospheric iron pool and the number of organisms that have lived and died, and conclude that any given biological iron atom has cycled many times through other living things. The arithmetic is sound. The exact history of a specific atom is not. The bomb pulse dating of cardiomyocytes by Bergman and Friesen is solid. It has been replicated and refined. There has been some scientific dispute about exactly how fast the turnover is, especially with age, but the basic finding that the human heart slowly replaces some of its muscle cells in adulthood is well established. So 3 of the 4 claims in this story rest on robust evidence. The 4th is statistical inference from sound premises. I would not want you to walk away thinking the whole story is speculation. It is not. It is mostly very ordinary physics and biochemistry. The strangeness is not in any single fact. The strangeness is what happens when you put the facts in a line. And now I want to make one last comparison, because I think it is the part that should be said out loud. The iron recycling system in your body, the one that includes the macrophages of your spleen and the hepcidin produced by your liver and the ferroportin channels in your gut, is doing the work of an entire pharmaceutical category. There is a multi-billion-dollar global industry built around iron supplements. There are intravenous iron formulations that hospitals administer for anemia. There is a drug called erythropoietin, which the kidneys make naturally to tell the bone marrow to produce more red blood cells, and which is sold as a recombinant protein for tens of thousands of dollars per patient per year, for people on dialysis or undergoing cancer chemotherapy. I am not saying the drugs are unnecessary. They are necessary. Some people lose more iron than their recycling can keep up with, and the supplement industry exists, in part, for them. Some people have damaged kidneys that no longer make erythropoietin, and the recombinant drug saves their lives. The dose of the natural system is mild. The dose of the pharmaceutical version, when needed, is targeted and large. There is no overlap to be embarrassed about. What I am saying is, the molecular machinery is the same. The drug erythropoietin acts on the same receptor in the bone marrow that your kidneys talk to every day. The intravenous iron is loaded onto the same transferrin protein your gut already uses. The pathways are not different. The drugs are just louder versions of what your body, free of charge, has been doing for you since you were in the womb. And the body's version was put in place by evolution, working with the same iron atoms that came down out of supernovae, the same iron atoms, more or less, that have already done shifts in countless other bodies before yours. You are not running on borrowed energy from the pharmacy. You are running at the molecular level on Stardust, managed by a hormone that costs your liver almost nothing to make. There is an old line, you have heard it, from dust to dust, ashes to ashes. People say it at funerals. It is supposed to be a humbling thought. The body returns to the ground. The flesh decays. We come from nothing and we go to nothing. But that is not what the chemistry says. The chemistry says you came from a star. The dust is older than the earth. The dust will outlast the earth. And every atom that was ever in your heart will in time go on to be in something else. A tree, a bird, a grandchild. The carbon you got from the bomb tests, the iron you got from the supernovae, the calcium you got from the second-generation stars, all of it gets handed on. Nothing is wasted. Nothing actually ends. That is not a sentimental thing. That is bookkeeping. The conservation of mass at low energies is one of the most boring facts in physics, and it is the reason for the whole story. The atoms persist. The bodies do not. From this point of view, the funeral verse is not a description of how small we are. It is a description of how large the cycle is, and how briefly each body gets to use a particular set of pieces. So, place a finger on the artery of your neck, the way you did perhaps at the beginning. Feel the pulse. Inside the muscle, producing that pulse, there is an iron atom, older than the earth, witness to oceans you never saw, to species you cannot name. It will not stay with you. None of them will. But for now, the supernova is in your chest, and the chest is beating, and the work is yours to do. That is the trip I wanted to take you on. If you have a thought about which atom in your body you would most like to have followed backwards, write to me and tell me. I would like to know which one you would have picked.